consider a very simple vibration problem. It consists of the uniform rod with a mass of 6 kg. Okay, that is attached to a spring of constant 700 Newton per meter. This is how the problem looks. It's a rod like this. Okay, so a uniform rod of mass 6 kg is attached to a spring of constant 700 Newton per meter. At the end B, the rod is depressed 10 millimeters and released. It's depressed 10 millimeters. It's depressed 10 millimeters. 10 millimeters and released. We want to determine the period of vibration and the maximum velocity at the end B. The period of vibration, we want to determine it, and the Vmax at B. So let's begin. First, as usual, we draw our free body diagram. So for this uniform rod, we have the following free body diagram. This. At the center, the gravity, the weight always acts. And that's the inclination angle theta. The distance from here to here is 0.1. The total length of the rod is 0.8. And from here, length from here to there is 0.5. So we can write that this point C, in fact, we can write that there is a torque about here, which is I, alpha, that's acceleration, and then there is the MA here. So recall that the force F, we can write that the force F is equal to kx plus static deflection, which is k is equal to 0.5 theta plus static deflection. Question comes, why do we have 0.5 theta? We have 0.5 theta because we are assuming a very small deflection, and at the same time we are assuming the okay, So because we are assuming a very small deflection, we are taking theta. Okay, and sine. The sine theta is equal to sine theta. Okay. So we can therefore write MA is equal to M Aruba alpha. What is that M? What is that R? What is that alpha? They are 6, the mass of the rod, R, the distance from the fulcrum to the center of gravity, which is 0.1, times double dot theta. And we can also write that the torque, the moment, is equal to one over 12. This for a rod, okay? 1 over 12 is the standard formula times the length of the rod, all square, then times alpha, which is theta double dot. This will give me 0.32 theta double dot. Having gotten these things together, what we want to do next is to write the equation of motion. Okay. So writing the equation of motion, we've gotten the moment of inertia times the acceleration I alpha. We've gotten it to be this. We've gotten the MA, that is the movement at the center of gravity, which is the mass times the acceleration, then times the radius of rotation. Now we want to determine the equation of motion. To do that, we are going to take the summation of all the moments clockwise at point C and equate it to 0. Okay, so let's go. Sum of moment at point C. If I stand at point C, okay, so if I stand at point C over here, if I stand over here, I have the weight is acting downwards. The moment will now be the weight W times 0.1 minus this upward force, and everything will be equal to the torque and the moment and the other moment on this point. Okay, so let's sum up all the moments now. So we will have W times 0.1 minus F times 0.5 is equal to, remember we still have, is equal to that plus this standard. Okay, we've gotten this, we've gotten this. So if we put these things into the equation, we would have it to be W times 0.1 minus F is equal to K 0.5 theta plus static deflection times 0.5 is equal to 0.32 theta double dot plus 0.6 theta double dot times 0.1. But when we are in equilibrium, as we saw, when we are in equilibrium, if we take the moments in equilibrium, remember we no longer have x, that deflection x. We are now going to have W 0.1 minus K static deflection of the spring times 0.5 meters. Which is equal to 0. And it's equal to 0. Let me take you to the drawing so you can see this. So we have in equilibrium there will be no x, is it not? So we have K times static deflection is moving in this direction and the weight is coming in this direction. Okay? And this K, the force is the K static deflection. While the moment we are taking is the distance from here to here, that's 0.5. That's how we arrived at that one. So everything will turn out to mean that minus K 0.5 squared theta is equal to 0.32 plus 0.606 theta double dot. Hence, our equation of motion turns out to be minus 700 0.5 squared theta 0.38. Sorry. Okay. .38 theta, which is theta double dot plus 460.53 theta is equal to 0. This is the equation of motion. Okay, this is the equation of motion. Okay.